Hello friends, today in my first video I will try to explain you short-term thermal capability of conductors by using two different international standards. One is IEEE, one is IEEE, and also of course it will give the same results. Here you will see the formulation for two different approach, and the basic formulation is the cross-sectional area is the root of ampere square and multiply by time duration of that short circuit and divided by a coefficient. This coefficient factor, K factor, is dependent on material of that protective conductor, for example, copper, aluminium, or steel. It is different. So what is dissipated energy? I square multiply by R and multiply by T. So it will give us volt ampere and second. So volt ampere is watt. If we multiply watt with second, we will find joule. Simply, if you give the energy to any metal, it will increase its heat. This is the main principle, I mean. So up to a certain degree of temperature, before its melting temperature, we will try to find its final temperature of that conductor with the given certain conditions. And also, I want to give you a very different approach, comparison of different short circuit energy dissipations. 16 kiloamp and 3 seconds. Comparison with this one, 25 kiloamp, 1 second. So 16 kiloamp squared of this one with 3 seconds and 25 kiloamp squared of this one and 1 second. As you see, 768 kiloamp square second is bigger than 625 kiloamp square second. It means that 16 kiloamp and 3 second requires more thickness than 25 kiloamp 1 second. Maybe the kiloamp level is more in the second case, but because of the total equation, duration of the time is also affected, square of the short circuit is also affected. That's why you will see the difference. Even I will show you in calculation tool. It's very easy, very flexible for you. And what are the required parameters for short-term thermal capability of conductors? Firstly, we need to know the initial temperature of the cable. If we are using a cable, for PVC cable, it is generally 70 degrees. And if we are using cross polyethylene cables like XLPE, then the starting initial temperature you can select as 90 degrees. Final temperatures of PVC cable is 160, and for XLPE 250 degrees. So you can use all these values for low voltage power cable calculations or medium voltage power cable calculations. On the other hand, that international IEEE standard defines also some limitations. As you see, we cannot use up to the, let's say, 600, 700 degrees for final temperature. Of course, we know that the melting temperature of the copper is maybe more than 1083, 84 Celsius. But according to international standard, it says that if it is in visible area and restricted area, and if you are using copper, your maximum allowable temperature is 500. If you are using aluminium, then it is 300. If you are using a steel, then it is 500. In normal conditions, all of them are 200 degrees. If there is fire risk, then all of them are allowed up to the 150 degree. So you will see all these things in this calculation tool that it will show you if it is convenient or you have to resize your conductor. Again, required parameters for short-term thermal capability of the conductors. Duration of the short circuit current you need to know. Up to 5 seconds these formulations are working. By the way, if you want to see a subtransient case up to, let's say, 2 cycle, 3 cycle, it means that if you are working in 50 Hz, 1 cycle gives us 20 milliseconds. If I am talking about 3 cycle, it is 60 milliseconds. Then you can examine 60 milliseconds or 100 milliseconds or, for example, 200 milliseconds. When can we use 200 milliseconds? If we are trying to size medium voltage power cables, let's say, then we can use this one. Why? Because we have a protection relay in behind side, and this protection relay can be set easily up to 200 milliseconds. Then there is no need for us to resize our cable up to the 1 second, 2 seconds. These are very, very long durations for them, and it will not be feasible. So for an optimum solution for medium voltage power cables, you can use up to 200 milliseconds. Then you will need to see what is the difference in this calculation tool, because in subtransient and transient cases, you will see the effect of X over R ratio. That's why I added additional part to this tool. What is that additional part? Joule integral. I will explain in further chapters. And short circuit RMS value in kiloamp. Of course, everyone knows this one. Okay, what is 16 kiloamp, maybe 25 kiloamp, maybe sometimes 40 kiloamp. It depends on the project requirements. Okay, let's pass through. Before calculation of the tool, I want to say to you that this is a very flexible tool, the Excel tool. You will download, you will easily use this one, and you will also compare 3 different calculation results. For example, one is copper, one is aluminum, one is steel. All these calculations can be adjusted with different duration, different initial final temperatures. Then you will be available to understand the difference of between each of them. Okay, what is required minimum thickness for me for that conductor? Let's pass through the Excel calculation part. As you see, this is the Excel tool to calculate minimum cross section of that conductor for short-term thermal capability. In column B, C, and D, you will see 3 different calculations. So for the first one, whatever you see here in yellow color, yellow highlighted one, it means that you need to adjust them. Okay, first let's start with the first row. Maximum allowable temperature. If there is a fire risk, you will select this one. And if maximum allowable temperature in normal conditions, you will select this one. As you see, this 200 in row number 7 changed to 200. It was firstly 150. Let me show you. Okay, do you see? 150. So if it is visible and in restricted area, then your allowable maximum temperature is 500. So the first one is like this, 3 different cases. The second one, conductor metal type. From here, you will see copper, aluminum, steel, lead, bronze, stainless steel, iron, silver, so many of them. I will explain later on that what are the meaning of these ones, because we will use for future conductor calculations, OPGV calculations, shield wire calculations, and so on. So the second one, let's say selected here as normal conditions, then you will see 200. Aluminium. The first one, we can select fire risk and steel. Okay, all of them are 20 kiloamps. By the way, we are writing here ampere units. That's why you will not write 20, you will write 20,000. Short circuit duration, okay, let's adjust it 2 seconds, 2 seconds, 2 seconds. And initial temperature, suppose that we are using PVC cable, 70, 70, 70. Then the final temperature, of course, we need to select 160, 160 and 160. Okay, let's see the results. The first one calculation result is at row number 24. We need 246 millimeters square for this copper cable. If we are using aluminum, then we need 371 millimeters square. If we are using steel, we need 676 millimeters square. Even it is not suitable because exceeding allowable temperature. So what was our allowable temperature? 150. Why? Because there was fire risk here. Then okay, I am changing it to 150. Then it is convenient. As you see, 712 millimeters square. Up to now, I explained to you for normal steady state short circuit conditions and what are the required minimum thickness cross sections of the cables. Let's pass through the other calculation which I showed you for 16 kiloamp, 3 seconds, as you remember. Comparison of this one with 25 kiloamp and 1 second. Okay, select the same things for each of them. Okay, aluminum, aluminum, and also let's say normal conditions, 3 second and 16 kiloamp, 1 second, 25 kiloamp. Initial temperatures and the final temperatures are the same. Let's see the cross sections. As you see, even if we are using 16 kiloamp with 3 second, because of that 3 second actually, the required energy capacity joule is more than this part, more than this 25 kiloamp. That's why at the first column number B, we need 364 millimeter square thickness, while in 25 kiloamp even the short circuit level is higher but the duration is less. Duration is only 1 second. The total required millimeter is 328 millimeter square. So as we see, this is less than the first one. So it doesn't mean that if we have a higher short circuit level we will need more thickness. No, it depends on the time duration together with the short circuit and the square of that short circuit, because this is the basic definition of energy dissipation. Okay, in the next chapter we will start what is subtransient cases and what are the difference in that Joule integral and what is the effect of that Joule integral for determination of cross sections. You will find a very detailed information in IEEE 60909. This Joule integral. You will see all these detailed, complicated formulation and what is Joule integral. Okay, let me briefly explain you what is Joule integral. X over R ratio, this effect gives us additional energy. Why? Because any of the short circuit is not in steady state firstly. They are in subtransient and transient cases. In subtransient case, it starts with a very high level, then slowly it reduces to the steady state level. That's why in the initial case, initial short circuit, we have much more short circuit amplitude compared to the transient, compared to the steady state cases. That's why kiloampere square second value is much greater than the steady state short circuit current. Due to this higher dissipated power during short circuit in this subtransient firstly and transient cases, required cross section is higher than normal calculation result. So how can we use this one? We can use in generator circuit breaker sizing calculations or in medium voltage power cable sizing up to 150 or 200 milliseconds as an industrial practice. As I explained it before, since you can set your protection relay up to 200 milliseconds, and in this 200 milliseconds, you need to be sure that, okay, what is the required kiloampere second value for that initial part? It is not the same as with steady state cases. And while using this Joule integral, make sure that the initial short circuit divided by the steady state short circuit should be at least equal to K value. So what is that K value? K is the peak short circuit current coefficient. I will prepare for you another video only to explain peak short circuit current and what is the relation between this peak short circuit current level and X over R ratio, DC components, and so on. Okay, it will be evaluated in different chapter. Only in this chapter I want you to focus on Joule integral. If we are working in a very initial cases up to the 100 and 200 milliseconds, for sure X over R ratio will be very effective. If we are working in less X over R ratios with 10, maybe 15, then you will see that the required kiloampere second value will be much less. But of course, it will be greater than again with the steady state cases. If you increase the X over R ratio, it means that you are working with a 500 MVA power transformer just in front of you. You are working and there is a short circuit there. Then the X over R ratio is most probably maybe 60 to 70. It means that the initial short circuit current will be very high. The peak short circuit coefficient will be maybe up to 2, because its limit is 2. 2 multiplied by square root of 2, then it will give you nearly more or less 2.77. So if it is too high, 2 times more than the steady state short circuit current, of course you need much higher cross section in this Joule integral part, in this 100 and 200 millimeters square. So I will show you in Excel tool how will we use this Joule integral. As you see, there is an example of Joule integral, and here a fault current is up to 1 second, but after 500 milliseconds it reaches up to 12 kiloamp. But I want to observe only subtransient part. As you see, this part, like up to, let's say, 100 milliseconds here, and this current level is too high, starting from maybe 17 till to 22 kiloamp. So it will give me a very different result compared with normal steady-state short-circuit calculations. Why? Because total dissipated energy here is much more than this one. It is directly proportional with I square and T. So let's come to one example and let's analyze what is the difference between this subtransient calculation required cross-section for a conductor. Before starting Excel tool, I want to show you here a picture of asymmetrical fault current. As you see, the initial short circuit level is to 20, maybe 22 kiloamp. As you see here, it is like 22 kiloamp, but it reduced up to 12 kiloamp. So if we are using this tool, I mean the first section of this tool, for sure I will write 12 kiloamp. But if I am using, let's say, up to 200 millisecond level, if we are working in this area, let's say we are sizing our MV power cables, then we need to see the effect of all these parts. As you see, all these parts. That's why it's a Joule integral. It's like this. I mean, this is and is equal from 0 to 200 maybe, because it is 200 millisecond. Okay, as you see, what I need to do is ampere square multiplied by T. That's why it is Joule integral, the sum of all these ones. And as you see, this part is much higher than this 12 kiloamp. So let's see the effect of Joule integral for subtransient and transient cases. Again, we are in our Excel calculation tool for short-term thermal capability of conductor. Firstly, from the down part, we will come to Joule integral page. Okay, in this Joule integral page, if I make it like this smaller, you will see so many things here. These are directly coming from international standard calculations. But I will tell you a very simple thing. Firstly, in row number 2, you will see X over R ratio at fault location. Let's start with 20, okay, for the first calculation. We are working in 50 Hertz network, and initial short circuit current divided by steady state short circuit current. What I wrote here should be at least same or bigger than the peak short circuit current coefficient. So I will define it in later stage, because you need to know what is M and what is N coefficients. So M coefficient is here 0.02 and N coefficient is here 0.35. According to these requirements, you will come through here and you will find from the graph, okay, what do I need for initial short circuit current divided by steady state short circuit current. The first one is 1. The second one is 1.25, 1.5 to 2.5. Okay, I will show this one later stage. You don't need to go so advanced level right now. As of now, let's say put it 2.5. Okay. Firstly, I want you to come to conductor sizing page again. Okay, we are working in the first row, row number B, because this Joule integral is working only in row number B. I didn't put it in row number C and D. everything is the same. Aluminium, 16 kiloamp. Okay, 3 seconds. Initial temperature is 70. Final temperature is 160. By the way, firstly, let's do this one. 0.1. Okay, we are working in transient, subtransient cases. It means that 0.1, 100 millisecond, up to 100 millisecond. As you see, if I am using normal cases, it means that steady state short circuit current, I need only 66.5 millimeters square conductor. But if I take into consider this transient, subtransient case, X over R ratio effect, the DC component effect, then the total required millimeter is 84 millimeter, maybe 30% more. Let's come through again Joule integral page and increase the X over R ratio. By the way, please keep in your mind 66 and 83. Okay, let's make it 60. We are in front of a very big power transformer like 400 MVA, 500 MVA. Okay, then our X over R ratio is 60. And do you see? Right now, the Joule integral result is 102 millimeters square, nearly double. So, from here, you can change the duration 0.2. Even this is also subtransient and transient case. So, if I am trying to size medium voltage power cable, instead of selecting 9 to 4, I need to select 131. Because there is X over R ratio effect. Maybe we are working, not maybe, let's say in power plants, unit auxiliary transformers, we are working in front of the unit auxiliary transformer, and for sure we will have an X over R ratio, maybe more than 30, 40. Then you will need to select, instead of 94, 131 millimeters square. This is just because of this DC component effect, because of Joule integral effect, because of, let's say, short circuit square multiplied by T, but this T duration in each millisecond, your kiloampere value is coming from a very high level. That's why I just kindly suggest you, while sizing your MV power cables, medium voltage power cables, please try to use this one. I mean, this Joule integral. For all other cases, like 1 second, 2 second, 3 second calculations, okay, you can use the normal tool. Okay, let's continue for the next step. As I told you, there are two different coefficients in Joule integral, M and N, and by using these two of them, we can determine initial short circuit current divided by steady state short circuit current, this one. Okay. By the way, by chance I wrote it 2.5 for these given cases. Let's say X over R is 60, our frequency is 50, and time duration is 200 milliseconds. It directly comes from the first page, conductor sizing page, and short circuit level. Okay, let's firstly look at M and N values. M is calculated here, 1.17 something, and N is calculated here in orange, 0.75. So I will show you here 0.75. Okay, firstly let me make it a little bit smaller for you to see much better. Okay, what was our time duration? Let me select this one. Okay, our time duration was 200 milliseconds. So up to 200 milliseconds, N value was 0.87. Okay, N value is 0.87 here somewhere. Okay, if we come to here till to here, as you see, we will find this one. Okay, so what is this value? As you see, 2.5. So initial short circuit, this is this one, divided by steady state short circuit, I need to put 2.5. That's it. That's why, in this calculation, I am writing here initial short circuit current divided by steady state short circuit current should be 2.5. Then you can return to conductor sizing page. Okay, what was the required, let's say, millimeter square here? Then you will easily find this one. Okay, the blue one. By the way, in Joule integral page, for a very precise determination of this initial short circuit current divided by steady state short circuit current, you can use also numerical analysis method. You will see easily from here, okay, how can I select this one more accurately and so on. Then you will see after 2-3 steps it will be okay. Then you will have a very great accurate calculation. I hope now you understand what is Joule integral and where it is used. In this part of video, friends, I will try to explain how I created this tool. Actually, it took too much time for me because there are so many different types of metals which I used, and for each of them, what are their thermal capabilities and so on, their coefficients. So it's not only included in copper, aluminum, and steel. Also, most of them, all of them I tried to put. So what is IACS? It is International Annual Copper Standard. It means that, in this Excel tool, I used as reference metal book this one, ACM International. Okay, in this metal handbook, you will see any kind of coefficient, that K coefficient, for that short circuit, short-term thermal capability of the conductors. I put all of them. So why did I put? Because we don't have a pure conductor in our hand. For example, we are working in a transmission line and we are using with a rail conductor. Okay, a rail conductor is composed of with somehow aluminum, and inside of that one there are some steel parts, okay, steel wires. So if I know the IACS percentage of that conductor, I can easily calculate what is the required minimum cross section for me if I am using a rail conductor in a transmission line. In the next slide, let's calculate one of them by using this IACS percentage value and what is the difference between a pure aluminum of this conductor and transmission line conductor. Okay, we will see. Here, this is rail conductor. I just find it from internet, one of the website, and just to see it is IACS value. As you see in the notes, they are mentioning 61.2% IACS value, so International Annual Copper Standard, and 8% for its steel part. So how will we use this one in our Excel calculation tool? Let's see. Again, we are in our Excel calculation tool, and I just want to show you in column number B and C the maximum allowable temperature, visible and restricted area, because we are working in a transmission line. Okay, both of them are the same. So the first one, since I am using rail conductor, as you see there are so many things here. I will try to find this one, aluminum alloy, and the 61% of IACS. So this is not pure aluminum, as you see. Suppose that we have 31.5 kiloamp short circuit level in this transmission line and the duration is 1 second. And the initial temperature of the conductor is 90 degrees. By the way, it depends on the countries. If you are working in a Gulf countries, it can reach up to 100 degrees sometimes. Or if you are working in Europe, maybe it is 70, 75. So to be on the safe side, let's put it 90, okay? The maximum allowable one is 300, by the way. Do you see here? So I cannot put it here 500, 400, something like this. It has to be 300 according to international standard. Then let's see the result. As you see, I need, let's say, 309 millimeters square if I am using aluminum alloy, and IACS percentage is 61%. If I am using normal pure aluminum, then I will need maybe 10 millimeters square less. So I want to show you this Excel calculation tool, this part. As you see, all the material conductivities and everything's are here, and you will see all these coefficients here. But you don't need to deal with all these ones. You will only use this very simple and very flexible tool. I think you understood this one. And let's say for the steel part, if we have, let's say, 8%. By the way, if we don't have any 8% steel, what I have here, yes, 8% something. Okay, zinc coated steel rod. Okay, we can use this one also. What you need to know is that you will not need that 611 millimeters square. Of course, if you are using totally this steel wire, of course you will need this one. But firstly, what do you have in your hand? A rail conductor. Okay, if we are using rail conductor, and it means that we have in our hand maybe 500 millimeters square aluminum alloy. So it is more than enough, because it is much more than this 300 millimeters square. This is just, I want to show you how can you use this IACS percentage. Actually, if I have time in the following weeks or months, I will try to put here additional videos and additional sizing tools, Excel tools. So some of them are like this shield wire sizing, especially starting from the power plant side. This is very critical, and you need to consider line to ground fault, actually, not even three-phase fault or line to ground fault. Depending on the connection part of the ground of this power transformers, and you will see such kind of fault level will give you much more thickness, required thickness for this shield wire. And the next chapter will be maybe this insulator quantity calculations in these transmission lines. Basically, I will tell you an exact approach while using insulation and coordination standards, international standards. What are the required minimum disc insulator quantity in one string, considering also the elevation after 1000 meters, and how will we evaluate in a transmission line if we are working in a very high altitude, and so on. And another chapter that I couldn't see on the internet, CT and VT calculations. Of course, I saw most of them, but most of them were very simple, and I want to show you here different protection relay requirements. Let's say we are using power transformer differential protection relay, and its requirement voltage level is that one. So what do I need? Let's say 5P30, 5P20, and what is the knee point voltage level, and what is the required burden voltage, volt amperes, and what are the requirements to protect, and so on. So I will try to explain a very detailed advanced level, hopefully in the following weeks, regarding this current transformer and voltage transformer calculations. And also if you are working in a medium voltage level with a triangle connections, and what is the required ferro resonance calculation of that burden, that VT. Let's say somehow you will see, okay, yeah, 100 volt amps. So from where it comes, and what is the resistance value, and how will we calculate that resistance value for ferro resonance effect to prevent this effect, and so on. The next step, maybe most of you are very aware of this MVA method. By the way, I am also using this one so frequently. It's very effective and very accurate way to calculate short circuits. You don't need any kind of software for this one, but you can verify even with any software. I will not mention any software here, but you know most of them. Then you will see how accurately and how easily you can calculate any short circuit level. By the way, including not only the three-phase, line to ground, and line to ground fault calculations. Insulation coordination study. I think you know what I mean here. What is the required protection level of a surge protective device, surge arrestor? How we are defining its continuous operation voltage, rated voltage, and dissipated energy inside of that one. Classification, class 1, 2, 3, depending on the transmission line length, and where to put that surge arrestor to protect in front of that transformer or in front of that substation. Then I will try to explain this one, and also when it is required to put both sides or only one side of these underground cables to protect them. And there is one different chapter which I really like much: electrodynamic force calculations in air insulated substations. By the way, this is, according to me, one of the main chapters of being a power engineer. And you will see so many things there. Effect of auto recall loss. Okay, how will we define, how will we select a proper size of post insulator, tubular bus bar? Okay, what is the maximum allowable length of one tubular bus bar, considering its diameter, considering its length, and considering the short circuit level, because there will be a frequency, and how will we damp that frequency, why we are putting inside of that one additional one or two rail or conductors, not pheasant, maybe the other one, cardinal conductors, just to damp that national frequency. Then it will provide us a very good protection for dynamic cases, for short circuits, and you will see most of them. And why don't we use auto recalls in power generation side, generation feeders? Because of the synchronization issue, of course we cannot use that one. Hopefully in the following weeks and months, one by one, chapter by chapter, I will try to explain all these things, and maybe one more, sag and tension calculations. And if you are working in a company, I will suggest you to use PLSCAD Ultralight. It's a very light version and very easy version to use. But even together with that one, I will give you an Excel tool also. In that Excel tool, you will see what is the total length of the conductor, what is the required sag in that conductor, and what are our limitations in one transmission line, where to put one tension tower and the other tower, suspension tower. So what are those limitations? These are like temperature, these are like ground level, I mean inclined spans, most of them. Okay, I will try to explain one by one. So I hope you enjoyed today's video. Thank you for watching this video, and I hope it will be very useful for your future calculations. See you again.